Let's continue our lesson on differentiation rules for polynomial functions and exponential functions, particularly here in Objective 2, being able to derive and use the differentiation rule for exponential functions. So what comes to mind? What do you think of whenever you see the picture that is here on this slide? Sometimes students ask me, like, what is it that you Google in order to find these pictures? Specifically, I Googled "You are your own worst enemy." And this is one of the pictures that cropped up, because when I think of the derivative for e to the x, this is the kind of thing that comes to mind, and you'll see here in a little bit. So let's do a little investigation to see if we can come up with a picture for what the derivative of e to the x looks like. So we're going to fool our calculator into giving us an approximate graph of the derivative of e to the x by just using the limit definition. So f prime of x is supposed to be equal to, of course, the limit as h goes to 0. And we have the difference quotient here, the slope of a secant line. Well, as h gets closer and closer to 0, we know that this slope is going to get closer to the slope of the tangent line. So what we're going to do is just pick an infinitesimal value of h, just something really, really small. How about, I don't know, maybe something like 0.001, something like this. 0.001, that's pretty small. All right, so we're going to type this into the calculator thusly. So in y1, we'll type in e to the x. So y1 is equal to e to the x. And then y2, we're going to graph this difference quotient. And it's almost like this limit. I mean, it's not perfect, but it's approximating it anyway, because h is just really, really small. So in your graphing calculator, if you're using the TI one, you're just going to recall y1. And the quickest way to get that is to hit second and F4, and it pulls up a submenu where you can select y1. I'm just going to do this on Desmos. So on Desmos, I'm going to do the same exact thing, but I'm going to call my functions like f of x. So f of x, and then say that's equal to e to the x. And then for some reason, e is over here on the QWERTY keyboard anyway, and then to the x. All right, so there's the graph of that. I don't like the fact that it's red. I want my kind of derivative to be red, so maybe this one's pipo. Okay, that's good. All right, and then on my second line here, I'm going to graph this difference quotient with a really infinitesimal value of h. And I'll call that function g of x. All right, and then here's my equal sign. I need parentheses around that whole top. And it's like f of x plus h minus f of x, all of that over h. So I'll call up my function f of x plus my h value being really small, and then arrow out of that thing, minus my f of x. Right, and then we need to divide it all by that h value that we chose. So divided by 0.001. Wait, it didn't do anything? Here, let me hit enter. It still didn't do anything? Wait, is this thing broken? Here, let me come over here to edit this, and I'm going to turn this like red. Well, that didn't help, and maybe make it dotted. Okay, and here, let me kind of flick it on and off. Boom, 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 boom. Well, here, maybe I zoom in a little bit. Well, what does this mean? What does this seem to indicate about the derivative of e to the x? It looks like the derivative of e to the x is e to the x. And like I said, back over there on that initial image, it's like being your own worst enemy. The exponential function e to the x is super special in calculus because it's the only function that is its own derivative, as we're going to prove. But all other exponential functions, let's say it's something like 2 to the x, or even say 1/2 to the x, they're not quite their own derivative, but they are directly proportional to the original function the derivative is. All right, so in the next couple of videos, we're going to get to the point where we can actually show that the derivative of e to the x is e to the x.